Oh my gosh, the silo!
It's filled with water.
And there's a big hole in the side.
It's coming out with grain and water.
How much grain do you think will be left when all the water's gone?
I have no idea.
Do you have a friend that you can call that might be able to figure this out?
Oh yeah, I know this guy named Seamus O'Houlihan from UC Berkeley who's a professor in calculus.
That might help a lot. Can you go contact him?
Yeah, I'll do it right now.
Awesome.
Samson, your swing is trash. I'll show you how it's done. Oh, wait. You're lucky, Samson. I have a phone call. Yeah. I'll be right there.
Donald, Jimbo, this is what's going on. We're going to use rate of change to figure out how much time we have until all the water is out of the silo and see how much grain is remaining.
Okay. So, Mr. Arnside, your silo is a right cylinder. It has a radius of 10 meters, and the water is currently at a height of 17 meters. From my observations, the rate of change of the height of the water was decreasing 0.002 meters. And so, by using the derivative, we can find the rate of change of the volume to find out when the water is gone and how much grain is left over. So we begin by having to find we need the equation for the volume of the right cylinder, which is volume equals pi radius squared height. And so the radius is a constant, so we can apply that now. And 10 squared is 100. And so now we take the derivative of this equation. So the derivative of the volume equals 100 pi h dh over dt. And so now we can plug in what we know. And so we do not know yet the rate of change of the volume, but we do have 100 pi, and the height is 17, and the rate of change is negative 0.002. It is negative because it is decreasing. And so when we put it all together, the rate of change of the volume is negative 10.681. And so now we move on to and so we'll save this number for later. But we will move on to the grain. And so the silo has the same dimensions. A radius of 10 meters, but instead it has a height of 14 meters. And this one is decreasing at 0.001. And so once again we can use the volume of the right cylinder and find the derivative to find the rate of change of the volume. And so we use the same equation. And once again, the radius is a constant. So once again the radius is 10. And then we take the derivative once more. And then plug in what we know. Bringing the rate of change of the volume to a rate of 4.398. So we will also save this number. And so now we have to find when each of these silos reaches 0. And so we have to make an equation. And so for the first silo, the equation will be 17, which is the original height, minus the amount of water that is leaving, which was what we found here. And we have to find when it equals 0. And so just solve that equation. So move 10.681 to the other side and divide. And so the amount of days that it takes for the water in the silo to empty is 1.592 days. We move on to the grain, and it has a height of 14 and a exiting rate of 4.398. And once again, we're finding 0. And add to both sides and divide. And then it will take 3.183 days for the grain silo to empty. And so now with these equations, we can input how many days it will take for that to empty. So we use this equation and put in the x from the silo of water. And so you put that in for x, because x measures time. And when you plug it all in together, we get an answer of 6.998. And that is the height of how much grain there is. So 6.998 meters high of grain when all of the water exits the silo.
Why, thank you, Seamus.
No problem, Mr. Ironside. If you ever have a problem with rate of change, call me, Dr. O'Houlihan, UC Berkeley.
Alright, so Robert, we've been in the business for about 7 years now,
Right.
and business hasn't been doing very well.
No, not really.
The first years we were increasing, but we just started.
Yeah,
so, yeah.
we're the up and coming people.
Yeah, so, but we peaked at about 2010, and it's been downhill from there.
Yeah.
And our sales have been pretty steady from 2013 on.
Yeah, pretty constant.
Now, the problem that I see from this is that when you look at all the Tupperware companies, all of them are made of the same plastic,
Right.
of the same shapes. The only thing that really varies is the color.
Right.
So we have to find a way to be different from the rest of the companies.
And how do we do that?
I propose that we hire a calculus professor.
From where? What school?
Of course, the great Azusa Pacific University.
Oh, of course.
Yes, fine calculus.
Yes.
Fine.
So you were going to help us optimize the amount of volume we can get.
Yes.
Well, thank you.
So I'm gonna draw out what your Tupperware currently looks like unfolded, and so you guys buy a giant sheet of plastic, right?
Yes.
So the sheet of plastic you buy is 20 by 10, and then we need to find the maximum amount on the sides, upwards.
Okay.
So I also have a 3D model of what it looks like folded. I want to be able to fit it. I'm not the best artist in the
That was pretty good.
in the world. So we have x, 20, and then 10. Okay, so we have the basics figured out, and so we know that x cannot be. So what I have found out is that x has to be greater than 0, and x has to be less than 5. The reason for this is that if it's less than 0, that means that there's no side up, which obviously there is a side up. And then if it's greater than 5, then right here it's going to be like 6 and then 6, which so they're going to overlap, which is impossible.
Right.
And so
Not enough plastic.
yeah, an equation we can find from this is x times 20 minus 2x times 10 minus 2x. And so if we use the FOIL method to get these two, we find that it's x 200 minus 60x plus 4x squared. Now if we times x in, I'm going to flip this around because I wrote it the wrong way. We find, oh, this is v of x. So if we take the derivative, oh no, first, sorry, times x in. So it's 4x cubed minus 60x squared plus 200x. So if we take the derivative of this, we find that v prime of x is equal to 12x squared minus 120x plus 200. So that's the derivative. And so we need to factor this out. And so we can simplify first by dividing everything by 4. So we find that it's 3x squared minus 30x plus 50.
That's a lot better.
Yeah, so we can't go any further, so we have to use quadratic equation.
Okay. Of course.
Yes. And so we'll do this here. And so we have 30, which is b, right here. 30 plus or minus the square root of b squared, which is 900, minus 4 times a times c, which is 3 and 50. So we have this all over to a being 3.
Okay.
And so if we simplify this, we can find that it's 30 plus or minus the square root of 300 all over 6. And so once we plug it into the calculator, we find that this is equal to 7.887 and 2.113. And so we know that it has to be between 0 and 5, so this is the only answer we can use, 2.133, or 2.113. And so we cannot use 7.887. And so when we find this, we know that this is x. We can find that the measurements for your Tupperware to find the maximum volume is 2.113 by 15.774 by 5.774. And so if we multiply this all together, the maximum volume you guys can make is 192.45 inches cubed.
Wow. Thank you, Professor.
You're welcome.
That's a lot of volume.
That's a lot of volume.
John!
What's up?
Guess what I got at the farmer's market?
What?
Bananas!
What am I, some sort of monkey?
I also got carrots.
So now I'm a rabbit?
Pretzels?
Salted or unsalted?
What's my name again?
Dana, California.
Dana, California.
Wait, the eyebrows.
On fleek, John.
Of course.
Is the collar good?
You look good, Dana.
All right.
Go.
Good evening. Sorry for breaking up your coverage of two 20-year-olds in an apartment. I am Dana, California, and we have breaking news. There's a high-speed chase on the 134 freeway. It is a 2007 white Cadillac Escalade. We're going to cut it to Chuck Traffic for more details.
Well, if you see Chuck, if there's the criminal car is going to the left at 10 meters per minute
Of course.
and has a 200-meter head start on the police who are going at 15 meters per minute, we can find how long it will take the police to catch up by doing this equation. You put 10x plus 200 equal to 15x. You subtract the 10x to get 200 is equal to 5x. And you see that 200 divided by 5 is 40,
Of course.
which is x, which shows that it will take 40 minutes at the current speed for the police to catch up to the criminal.
So we're gonna be here a while.
Yeah, so we can also check to see how much distance is covered by the criminal also by doing an integral from the 0 to the 40 minute, start of the time to the 40 minutes that we just solved for,
Of course.
times 10 because that's the speed that the criminal is going, dx because it's an integral. We find that this is equal to 400 meters covered by the criminal before the police catch up.
Hopefully they have full tanks of gas. We just found out that from Dana, California told me that this car is slowing down because it just popped a tire.
Oh, okay, so we can, let me have the eraser. So we can see that since this, let's assume this tire blew,
Of course.
so it's now slowing down, right? So it'll be slowing down at 0.2x squared plus 1 per minute. So we can see that the equation to solve how much time it will take for the car to stop moving will be this equation, 10, which is the speed it's currently going, minus the 0.2x squared plus 1, we find to be equal to 6.708 minutes until this car stops moving. So we can use this to actually find out how far the car actually goes by doing the integral from the start of the time to the time that it stops moving that we just found right here, times the 10 minus the 0.2x squared plus 1 integral. And we find this equal to 40.249 meters, which is substantially less than the 400 meters we saw for earlier. By using this, plus by adding the 200 meter head start that the car had earlier, we can actually find out how long it takes the police to catch up. So we can put the speed, which is 15, let's say time is t, equal to the 240.29, which is the amount, the distance that the criminal car will travel. And then when you divide that number by 15, we find that it equals 16.017 minutes for the police to catch up. So now we can see the graph. I can make a graph of what this will look like. So we can find that the speed, the graph of speed, will look like, let's say this is 9, and this 1, 2, 3, 4, 5, 6 is 7. So this is the time in minutes.
Of course.
And this is the speed in meters per minute.
Obviously.
So initially the car will start off at 9 and it will slow down by the 6.078. So this number will be 6.708, comma 0. So that's when the car will stop moving. That's the speed. So now we can use this to solve for the graph of acceleration, or the position graph, excuse me. So by making this 200 and this 250, and this being 7 again and 6, we can see that when it starts at 200, the car will initially be going faster and will slow down to the 240.249 that we saw for earlier. So at this point, when it stops moving, it will be at 6.708, which is the amount of time it took to stop, and the 240.249 meters that it actually traveled. Yeah.
Well, thank you.
Like you can get your eyebrows.
On fleek, John.
Of course, of course.
Collar good, John.
Perfect.
You look great. You look great. And we're live.
Wow, that's some gripping stuff, Chuck. Well, we'll return you to your broadcast of two 20-year-olds in an apartment. Thanks for watching. I'm Dana, California, and this is the news.